In this lesson, we're talking about the simple harmonic motion. Let's go through its basics, definitions, concepts, and applications. Okay, so let's first understand the harmonic motion. So what is the harmonic motion? Let's take this free body diagram here. All right, so imagine we have this cube here with a certain mass that's attached to this spring, and the spring is attached to a wall, for example. Okay, the spring has a constant, this elastic constant. Okay, and well, we have the mass. So if we do the balance of forces here, we have the normal force and the weight. They're equal, they're the same in this case, okay? And imagine that the spring is stretched. So because of this, we have this force pointing in this direction to the wall, okay? That's because of Hooke's law, right? And at this point, we're holding the block here at this position, X, okay? Let's say that the natural position of the spring is here, x equals 0, but we're holding the blocks to the velocity 0. At the time we release the block here, we have this situation. Let's imagine the block reached its natural position, x equals 0. The force now is 0, okay, because we achieved the maximum velocity. Okay, we have this negative here because of our reference, right? But the block now achieves its maximum velocity. The net force is 0, and the position here is x equals 0. After this, the spring starts to compress. So we have kind of the same thing. We compress it until the block stops. At this point, the net force is the maximum, pointing the other direction. The velocity is 0. We have the space here. The place where the block is negative x. Alright? And the block starts to move again in the other direction. For the same motion, we reach the same situation here. Net force 0, maximum velocity pointing the other direction, and x equals 0. Right? And then after this, the springs start to stretch again, and we reach the situation, which is the same as the first situation. So for this scenario here, we have no friction, right? So if you have no friction and you do it with the springs, the motion just doesn't stop, right? We have the spring stretching and compressing, the block moving left and right, left and right. And for this motion, we say that's the harmonic motion. So for this motion, we have something that we call the period, okay? And the period is actually 2 pi times the square root of the mass of the block divided by the constant of the speed, okay? And we also have a frequency of this motion, right? As frequency is the inverse of period, so frequency is 1 over 2 pi times the square root of k over m. Now we can do a relationship between the harmonic motion just seen and waves. Well, imagine this block here attached to a spring, okay? Let's despise all the other forces we have. Imagine it's just the block and the spring forces. So if we stretch it and release it, we start a motion like this. Now let's put two axes here. Here is the space, so the block is moving up and down, and now it's moving over time. So if we plot this, we see this red line here. That's actually a wave. So we can relate the harmonic motions with waves like this, okay? And well, for this wave here, we actually have a space function for it. Okay, a space function of time, which is x. Remember, x is the position of the block, all right? Times cosine of 2 pi times t times time divided by the big T here, which is the period of the motion. Okay, this capital T is the period and the small t is the time. Alright, so we talked about velocity, about the space function. So we can, from the space function, derive the velocity, okay, the speed function, which is given by this formula here, is negative the maximum velocity times the sine of 2 pi times time divided by the period. This maximum velocity here, I'm not going to derive this function right now because, well, it's not interesting to us right now, but this maximum velocity we can calculate using this formula here. Okay, it's 2 pi times the position divided by the period, or the position, okay, times the square root of k over m. And also from this velocity, the speed function, we can also derive the acceleration. All right, that's negative k times x divided by m times the cosine of 2 pi times t, the time, over the period. Okay, so take a look at this image here. So that's what's happening actually. So let's first look at this first graph. That's the space function. Okay, as we've seen before, well, the mass here, the block, it's moving up and then starts moving down. So we have this harmonic motion here over time. Okay, that's up and down, up and down. For this, we have the velocity. Remember, when we were talking about the harmonic motion, at a certain point, we reach the maximum velocity. That's when the spring is in its natural position. Okay, and when the block reaches this position here, or this one, the speed is actually 0. Right, the block's not moving in these 2 points here. So we have this motion also, but related to velocity. And the same for acceleration. You can see the green arrow here shows the magnitude of the acceleration. So at a certain point, when the block stops, we have actually the maximum acceleration in the opposite direction of the motion, right? So every time the block is here in its maximum extension of the spring, or the maximum when it's compressed, we have the maximum acceleration. Alright, now let's practice real quick using these concepts. So we have a diver on a diving board that is undergoing a simple harmonic motion. The mass, her mass is 55 kilograms and the period of her motion is 0.8 seconds. Okay, and the next diver is a male and whose period of simple harmonic oscillation is 1.05 seconds. So you want to know what is the mass of this guy here, the second guy, if the mass of the board is negligible. Okay, alright, so let's apply this formula here for the period, because we have this information. Okay, we have also for the first diver the mass of the first diver, which is 55 kilograms. So by this we can actually find the constant, the elastic constant of the spring. All right, I said spring because it's acting like a spring, right? We know it's the diving board. All right, so applying the period and the mass, we can find the elastic constant, okay, which is around 540 newtons per meters. Now that we have the elastic constant for the diving board. We change for the male diver now, the second one, which is probably heavier, right? Because the period is actually greater. So we can calculate it. Now we can calculate the mass. Just add the values here, and we have a mass of 94.75 kilograms, which is heavier than the mass of the first diver. You can notice by the period of motion, okay? The fastest, it means that the mass is lower, actually. Okay, now it's our turn to think about it. Suppose you plug an acoustic guitar string, okay? And you hear a single note that starts loud and slowly quiets over time. So I want you to describe what happens to the sound waves in terms of period, frequency, and amplitude as the sound decreases in volume, okay? So in the guitar, when you plug the string here, is the same note, okay? The only thing that's changed here is the volume. So think about period, frequency, and amplitude of the string in this case, and tell us in the comment section.
What did you think about this video? We appreciate your feedback, so tell us in the comments section.